One interesting theory related to neutron stars is the strange matter hypothesis or strange quark matter hypothesis. This theory suggests that under the extreme conditions within a neutron star, quarks, which are elementary particles that make up protons and neutrons, could combine in such a way that they form a new type of matter called strange quark matter. The strange quark matter hypothesis proposes that this strange matter could be even more stable than the dense neutron-rich material found in neutron stars. If this is true, it could have profound implications for our understanding of the fundamental forces of nature and the stability of matter. The idea is that strange quark matter could be the true ground state of matter, meaning it is the most stable form of matter in the universe. If it is more stable than the matter we are familiar with, then neutron stars, and perhaps even normal atomic matter, could eventually convert into strange quark matter given enough time. This theory has generated a lot of interest and research within the field of astrophysics and particle physics. However, it's important to note that the strange matter hypothesis is still highly theoretical and speculative, and there is no direct experimental evidence to confirm its existence. Researchers continue to study neutron stars and conduct experiments to better understand the properties of matter under such extreme conditions. Neutron stars are found throughout our Milky Way galaxy and in other galaxies as well. They are remnants of massive stars that have undergone supernova explosions. Neutron stars can be difficult to observe directly because they are small, incredibly dense, and emit primarily X-rays and gamma rays. They are often discovered through indirect means, such as their gravitational influence on nearby objects or by observing their electromagnetic radiation in the X-ray and radio spectra. Neutron stars are typically located in regions where massive stars have gone supernova, so they can be found in various locations within galaxies. They may also be part of binary systems, orbiting another star, which can make them easier to detect. Some well-known neutron stars in our Milky Way galaxy include the Crab pulsar in the Crab Nebula, the Vela pulsar in the Vela supernova remnant, and the famous PSRB 1919+21, which was the first pulsar ever discovered. These objects are relatively close to Earth in astronomical terms, making them accessible for study. Neutron stars can also be part of X-ray binary systems where they accrete matter from a companion star, emitting X-rays in the process. Studying these systems has provided valuable insights into the properties of neutron stars. In summary, neutron stars are found in various locations within galaxies, particularly in regions where massive stars have ended their lives in supernova explosions. They can be scattered throughout the Milky Way and beyond. The distance of neutron stars from Earth varies significantly depending on their location within our Milky Way galaxy. Neutron stars can be relatively close or quite distant. Here are some general guidelines. Closest neutron stars. The nearest known neutron stars are typically within a few hundred to a few thousand light-years from Earth. These relatively close neutron stars are more likely to have been discovered and studied in detail. Distant neutron stars located in other parts of our Milky Way galaxy can be tens of thousands to tens of millions of light-years away, or even more. These more distant neutron stars are much more challenging to observe and study. Keep in mind that the Milky Way galaxy itself is vast, with a diameter of around 100,000 light-years. Therefore, the specific distance to any given neutron star will depend on its location within the galaxy. The distances to neutron stars are typically determined through a combination of methods, including measuring their parallax, the apparent shift in their position as seen from Earth due to our planet's orbit around the Sun, their proper motion, how fast they move across the sky, and other astronomical techniques. For the closest neutron stars, their distances can be measured more accurately, while for more distant ones, estimates may be based on less direct methods, introducing greater uncertainty in the distance measurements. Neutron stars themselves are incredibly distant from Earth, and they do not pose any direct danger to our planet or to human life. In fact, the nearest known neutron stars are many light-years away from us. For example, the closest known neutron star, PSR J0108-1431, is over 400 light-years from Earth. Neutron stars are incredibly dense and have powerful gravitational fields, but they are not a threat to us because of their great distance and because they do not emit harmful radiation or possess any means of affecting Earth directly. However, it's important to note that the processes that lead to the formation of neutron stars, such as supernova explosions, can have significant effects on a cosmic scale. A supernova occurring in our galaxy could produce a burst of high-energy radiation, but for it to pose a direct danger to Earth, it would need to be extremely close, which is highly unlikely given the vastness of the Milky Way. In summary, neutron stars themselves are not a danger to our planet or to human life due to their remote locations, and their natural formation processes, like supernovae, would only be a concern if they were to occur in close proximity to our solar system, which is exceedingly rare.